So we've been learning about Dalton's law of partial pressures where you have a mixture of gases. And so before we take a look at how we apply that to a real laboratory example, I want us to watch a little animation. So um, pay attention to this, how we collect the gas over water, and then we'll look at a diagram that's in your notes that a handout that I gave you.
Potassium chlorate, KClO3, decomposes to potassium chloride, KCl, and oxygen gas, O2, when heated. Manganese peroxide, MnO2, is added to speed up the reaction. The oxygen gas produced in the reaction can be collected by bubbling it through water and collecting it in a bottle or graduated cylinder. As oxygen gas is generated, the gas bubbles rise to the top and displace water from the cylinder. This method of collecting a gas is based on the assumptions that the gas does not react with water and that it is not appreciably soluble in it. The oxygen gas collected in this manner is not pure because water vapor is also present in the cylinder. The total gas pressure is equal to the sum of the pressures exerted by the oxygen gas and the water vapor. Consequently, we must allow for the pressure of water vapor when we calculate the amount of O2 generated. The partial pressure of O2 equals the total pressure minus the pressure due to water vapor.
Okay, so what we just watched was showing you how we would collect a gas by water displacement. So this is the handout that I've given each of you. And if you take a look, this is the same setup that we had on the previous animation. So let's look at how Dalton's law can be applied to this. So we're collecting oxygen gas. So as this substance here is heated, the potassium chlorate, the oxygen gas, I'm going to let this be represented here by the little red dots. So this is the gas traveling through this little tiny tubing. And as it is being collected here, it will bubble up through the water and eventually make its way to where it will push the water out. So we're collecting oxygen here. Okay, in our canister. So the oxygen has a partial pressure. Now, since we have water also that we are using to displace so we can collect the oxygen gas, you're going to have some water vapor. So I'm going to represent, the little blue dots are going to represent water vapor, H2O, in the vapor state. So I'm going to put just a few of those. And of course, the pressure of the water vapor will be dependent upon the temperature at which the gas is collected. So in our animations where we've been looking at a mixture of gases, I'm going to put a box around this section where we have our gas collected. This represents the area or the space in which you have both oxygen and water vapor. So Dalton's law says that the total pressure in this container, we would write that formula as P total, is equal to the partial pressure of the oxygen plus the partial pressure of the water. Now, if we're collecting the oxygen, that's the one we really care about, specifically his pressure. We need to isolate the P of O2. So if you just mathematically solve for the X here, which is your P of O2, then this formula then becomes pressure of O2 is equal to the P total minus the pressure of water, because we have to subtract out the water vapor. This is the form of Dalton's law that we will be using to isolate the partial pressure of the gases we collect. Now, normally, once you get the partial pressure of the individual gas, you would plug that pressure into a gas law. So like you could then plug it into the ideal gas law, or you could plug it into the combined gas law. But you typically will find the pressure of the individual gas. You will determine that using Dalton's law. Once you isolate the pressure of the gas, you will then plug it into another gas law. Now you may be wondering, where are we going to find the pressure of water? Well, the handout that I've given each of you has at the bottom of it, it has the vapor pressure chart. So the vapor pressure chart here has the vapor pressures of water, at various temperatures ranging from -10 degrees Celsius all the way to 101 degrees Celsius. Do pay attention that these pressures are in torr, and so you need to make adjustments depending on the gas law you were using if you were need to make sure your units are in agreement with one another. Now, in your gas law problems, the way you will know that you have to use this formula first is you will see key phrases like a gas was collected over water or a gas was collected by water displacement. And that's when you would know you need to subtract off the water vapor. All right, so this is our little introduction to collecting a gas by water displacement. On the next little video, we will take a look at some problems using this concept.